In this video, we're going to define a cycle, a thermal reservoir, and a reversible process. So we'll start with a cycle. A cycle we'll define as a series of processes that return to the initial state. So what do we mean by that? Well, let's look at a diagram of our system, and we have a state 1 that has a set energy level. Energy 1 has a pressure level. Well, if we take that state and that system, we have it go through an energy transfer. It goes through a process. We'll call that process 1-2. Goes to state 2. Well, then if we put it through another process, we'll call process 2-1, that brings it back to that initial state, then this is a cycle. So we've had enough processes that bring it back to our initial state. That makes it a cycle. If we look at the energy balance of a cycle, we have that the change in our total energy transfers should equal our change in our energy. Well, if we look at a cycle, as you can see from the diagram, it comes back to the initial state, energy 1. So the delta of that energy at the state is 0. So we're going to cancel that out, and we can say that the heat transfer for a cycle is going to equal the work for a cycle in all cases of a cycle. When we talk about thermal reservoir, we say that it's a system that remains at a constant temperature even though energy is added or removed. An example of that would be, let's look at Lush reservoir. If you were to take a cup of coffee and dump the cup of coffee into Lush reservoir, the average temperature of Lush reservoir is not going to change. Okay? It is a large enough system that even if you're dropping ice cubes, 1 or 2 ice cubes, or we drop a cup of coffee, you're not going to affect that system. Okay, we can kind of just treat it like it's just going to stay constant out there. Right? So when we look at thermal reservoirs, we'll look at a power cycle as an example. The temperature that's higher is going to call our high temperature reservoir. The temperature that's lower, our low temperature reservoir. We denote that with a T sub H and a T sub L respectively. The heat transfers, it doesn't depend on the direction or how much. It just depends on where that heat transfer is coming from. So if the heat transfer is coming from or going to that high temperature reservoir, it's going to be the high temperature heat transfer. Okay. So it's always going to be the one that's associated with its reservoir. Likewise, the low heat transfer is going to be associated with the low thermal reservoir. And then work net is just the total net work that is associated with this cycle. It can be either positive or negative depending on if it's going into or out of the system. Now, a reversible process we define as a theoretical process in which the system and its surroundings can be returned to their initial state. It is completely theoretical. It's ideal. It doesn't happen in real life. If we look at an example, so we have a system that the air inside it has a mass on side of it. The mass gets lowered, the system rises, has some moving boundary work. If we then increase the mass again, bring it back down, well, if the amount of energy that was created from the moving boundary work, if we could bottle all that up, if we could capture it all and put it back to make our process go from the second state all the way back to the first state, well, then it would be reversible. But the problem is we're going to lose some of that energy when we're going from state 1 to state 2. You're going to get some friction that's going to be lost along the way. There's going to be some energy you just can't capture. This is why perpetual motion machines don't work. Another way to describe a reversible process, it is a process that has no irreversibilities.